we're going to solve two continuity problems. In the first problem, it says determine all points of discontinuity for each function. Part A is a rational function. It's a fraction with polynomials. Rational functions are continuous on their domains, and the domain of a rational function is all numbers except for those that make the denominator equal to 0. That means the discontinuities have to occur when the denominator is 0. That's because we can't divide by 0, and the function is undefined at those points. So I set the denominator to 0, I factor in an x out, and then set the factors equal to 0, and I got two discontinuities, x equals 0 and x equal 1. Now x equals 0 turns out to be a whole, whereas x equal 1 is an asymptote. I know that x equals 0 is a whole because there's a common factor of x. If I had reduced, I could have lost that common factor of x. Anytime you have a common factor, it's a whole. Or as a side note, more formally, I know x equals 0 is a whole because if you try taking the limit as x goes to 0 of this function, you can cancel the x's out, you plug in 0, and you get -3. That means the limit exists, but the function doesn't. Whereas at x equal 1, if we take the limit as x goes to 1 of this function, we end up getting 3 divided by 0, which doesn't exist. This limit doesn't exist. And in fact, anytime you have a non-zero number divided by 0, that means it's going to go to either positive or negative infinity. There's an asymptote at x equal 1. Now the second function is a piecewise defined function. Each piece is continuous, but we have to check and see what happens at that split x equal 1. There might be a discontinuity if the two pieces don't line up. So on the left side of x equal 1, if I think about x values that are smaller than 1, or if I take the limit as x goes to 1 from the left, I would plug 1 into that top definition. If I plug 1 into x squared minus 2, I get -1. That means as I approach 1 from the left, the y values approach -1. If I approach 1 from the right, if I think about x values that are bigger than 1, and what happens as I get closer to 1, that means to find the limit, we plug 1 into the bottom definition. 2 times 1 minus 3 is also -1. This tells me the two pieces line up at x equal 1, and therefore it has to be continuous at x equal 1. The limit exists, and the function exists, and all of those numbers are the same. Example 2 asks us, what value should we assign to f of 2 to guarantee that f is continuous? This is another rational function. It's not continuous at x equal 2 because 2 makes the denominator equal to 0. This function is undefined at x equal 2, so it's not continuous there. For the function to be continuous at 2, the function value would have to equal the limit. And so I'm going to start by finding the limit as x goes to 2 of this function. We can factor the numerator as x minus 2, x plus 1. And then we can cancel that common factor of x minus 2 out. I'm left with the limit as x goes to 2 of x plus 1. If I plug 2 in for x, I get 3. That tells me as the x values approach 2, the y values approach 3. If I want this function to be continuous, the limit has to equal the function value. So if we assign f of 2 equal to 3, then the function value and the limit are all the same.